In this video, we will try to learn Reynolds transport theorem. So question is, what is the need of Reynolds transport theorem? Most of the physical laws like Newton's second law of motion or other laws are developed for fixed mass, or we can say are developed for systems. But in fluid mechanics, in many situations, we use the control volume. So there is a need to develop relationship between the control volume properties and system properties so that we can use the physical laws meant for system properties. This theorem, which relates system property to the control volume property, was studied by English engineer named Osborne Reynolds, who lived from 1842 to 1912. So in his name, this theorem is called Reynolds transport theorem. In this theorem, we shall discuss the simplest derivation with the help of this figure. In this figure, in some flow field, these are the two diverging lines, which may be fixed lines, or you can say these are the stream lines, because we know by definition of the stream lines, no flow can cross these stream lines. Fluid is flowing in x direction, and we consider section at 1 and section at 2 through which fluid is flowing with velocity v1 at inlet and v2 at outlet. This section 1 and 2 is enclosing some volume, which is shown here with the help of shaded region. This is the control volume by definition, and it is not moving here. And at time t, whatever mass is enclosed here, so it means that the system property and control volume property at time t is equal to same, which is shown with the help of this shaded region, right? This shaded portion enclosed between this line and this line. At time t plus delta t, what happens? This shaded portion was having some mass. That mass has taken this position now, enclosed between 1 dash and 2 dash, and shown with the help of these hatched lines. So this is the position of the mass at time t plus delta t. Right. Now look at two properties also. This area between 1 and 1 dash is represented by 1, and 2 and 2 dash, this 2 and 2 dash is represented by 2. What does this area represent? 1 and 2. This 1 represents the flow of that property through phase 1, or you can say that property, generally we talk about the extensive property. It could be the mass, it could be the momentum, it could be the energy, it could be the angular momentum, or it could be the energy. So this 1 is representing that property, extensive property, is going inside the control volume through phase 1. And what does this 2 represent? This 2 represents that extensive property is going out through phase 2, through this phase 2, out of this control volume, that is outflux, is represented by 2 and influx is represented by 1. Now after understanding this figure, we will write one equation at time t and at time t plus delta t. So kindly note down this figure properly. I am again repeating, this shaded portion is the control volume at time t, and this shaded portion is control mass at the time t. So at time t, both are same, means control volume is same by definition and control mass is same. At time t plus delta t, this control mass is shifted from shaded portion to this portion, which is represented by hatched lines, and this point, this figure number 1, portion number 1 and portion number 2 represents that property, extensive property going inside the control volume in time delta t, and this 2 portion is representing that extensive property is going out of the control volume through phase 2 in time delta t. Right. So after understanding this figure, we can write this equation that system property and control volume properties are same when time is t, and at time is equal to t plus delta t, this system property, what is system property? It is shown with the help of this hatched line, is equal to what? Control volume, which is shown with the help of shaded region, minus 1, this minus 1 and plus 2. So this hatched line is representing the system property at time t plus delta t, and now we want to relate this system property to the control volume property, and that can be related with the help of equation number 2. So I am again repeating, at time t plus delta t, the system property shown with the help of hatched line is equal to control volume shown with the help of shaded region minus 1. This represents property going inside the control volume through phase 1, and area number 2, portion 2, which represents property going outside the control volume through phase 2. Now keep this thing in mind. Now I am writing a general equation, slightly more general, where we are considering some extensive property and representing it by B. What is extensive property? Which depends on mass. It could be mass, it could be energy, momentum, energy, angular momentum, etc. And small b is called corresponding intensive property of that extensive property, let's say B. So B by M is known as intensive property. Now we know that extensive property is additive in nature. We can add and we can subtract. So at time t for the given figure, B system of t and BCV at t, both are same. At time t plus delta t, B system t plus delta t is equal to BCV t plus delta t minus B1 t plus delta t plus B2 t plus delta t. Now this is equation number 1, let's say this is equation number 2. So now we can write another equation by managing these two equations by 2 minus 1 divided by delta t. So 2 minus 1 divided by delta t. So left hand side of the equation is B system t plus delta t, this portion, minus B system t divided by delta t. And here this BCV at t plus delta t minus BCV t, this thing, divided by delta t, and b1 minus b1 t plus delta t divided by delta t plus b2 t plus delta t divided by delta t. Now, by using the definition of differentiation and taking delta t tends to 0, this equation number 3 can be written as dB system over dt is equal to dB Cb over dt minus this b1, which is equal to basically that extensive property going inside the control volume. So this is represented by b in dot, plus this is a plus b2. b2 is what? That property is going outside the control volume through phase. So that is represented by b out dot. So this is one form of Reynolds transport theorem, in which left hand side we have the rate of change of that extensive property for system is equal to rate of change of that extensive property for the control volume minus that property, extensive property, going inside the control volume through some phase, that is known as b in, and plus b out is representing that property is going out of the control volume through phase through some control surface, right? Now if we look at these two terms, minus b in plus b out, what does this represent? This represents the change in property through phase through control surface. So that is known as b net, what is happening at the surface. So at the surface, property is going out, that is plus, and minus going in, so minus b in. That may be written in terms of the integral at the control surface. So integral at control surface, b is the intensive property multiplied by mass. So b multiplied by mass of that infinity small control volume. So that is taken as rho b multiplied by, so m is extended like this, rho multiplied by v is a vector quantity, dot n is vector which is perpendicular to infinity small cross sectional area. So this represents b dot n represents dot product, and dot product is a scalar quantity which is explained here. So suppose we have a very small elemental area dA. Now perpendicular to this surface we have a vector n which is representing for this cross sectional area, and v is the corresponding velocity at this cross section, and theta is the angle between these two. So v dot n here, v dot n is magnitude of v, magnitude of n multiplied by cos theta, which is equal to v cos theta. So when theta is equal to 90 degree, theta is equal to 90 degree means cos 90 0, it means that fluid is flowing parallel to it, so its value is 0. When theta is equal to 0, when theta is equal to 0 means we have v in this direction, so theta is equal to 0, so it represents out. So when theta is equal to 0, cos 0 is equal to 1, this will be v, only v, so it will be plus sign. And when theta is equal to 180, if theta is equal to 180, then this will represent inflow. So in case of theta is equal to 180 degree, this will represent the velocity is going inside the control volume at 180 degree. So going inside, theta is equal to 180, cos 180 is equal to -1, so this will represent minus v. This is representing minus in. So inflow will represent minus and outflow will represent plus by taking care of this vector nomenclature. So these two properties, minus b in plus b out, or these two terms, which represents the flow across the surface, can be represented by b net, and this can be represented by this term, integral at control surface integral or surface integral rho b. B is the intensive property, corresponding intensive property, v dot n dA. Now with the help of this definition, the Reynolds transport theorem can be written in this format: dB system over dt is equal to d over dt control volume rho b d volume for infinitely small volume dV, and this b is the corresponding intensive property, plus this we have just discussed at the surface what is the net rate of flow of that extensive property, which is represented by rho small b v dot n dA. Right, this is the more generalized form of Reynolds transport theorem. Now we shall try to understand some analogous relationship between Reynolds transport theorem and material derivative, which we studied in our last video. In case of material derivative, we know that this material derivative relates Lagrangian description for following the mass to Eulerian description where our volume is fixed, and in this case we took infinity small volume. Infinity small volume means here we have a differential approach, and in this case, in case of RTT, our volume was finite, so we are taking integral approach, we are integrating, and this is RTT is relating the system analysis, means Lagrangian description to the Eulerian description, which is known as control volume analysis. So in this video we have learned the main derivation of Reynolds transport theorem, which relates system property to the control volume property, and we also learned the need of understanding the Reynolds transport theorem, and this was due to that in fluid flow phenomena in many situations we use the control volume analysis, but the physical laws are applicable for dynamics problem are related to system properties. So there is need to develop relationship between control volume property to the system properties so that we can use the suitable physical laws applicable in that particular situation. Now in last we just slightly discuss about the what is system and what is control volume, though in thermodynamics you have already studied this. So let's say this is a control volume. Through this control volume it can interact, and this portion is outside this surface is known as environment. So through this environment, if mass can come in and mass can go out, then this is known as control volume. And if we have volume which is enclosed through these surfaces and energy can come in, energy can go out, but mass cannot come in and mass cannot go out. So there is no mass interaction. Mass interaction is 0. Here mass interaction is not equal to 0. Energy can come in, energy can go out in case of the system, but mass, in case of system, mass transfer is 0. But in case of control volume, the mass can come in, mass can go out. This is the difference between system and control volume. Thank you.